Something impossible is happening in Israeli airspace. The infrared monitor glows bright in the darkness. A small cross-shaped targeting reticle tracks steadily across the screen, following the silhouette of an enemy drone cutting through the night. No sound, no warning. Just the soft hum of cooling systems and the gentle whir of servos adjusting aim. But there's no missile streak, no muzzle flash. Just a brilliant white light, exactly where the crosshair points on the drone's wing. The wing shivers and disintegrates. The drone tumbles, spinning wildly as it loses lift. As it plummets, the reticle shifts to the drone's main body, where the warhead waits. The explosion fills the monitor with debris and smoke. Technology has caught up with science fiction. Israel destroyed a drone using nothing but invisible energy, traveling at the speed of light. Light instead of bullets. The technology is called the Iron Beam, and it was born from the harsh realities of asymmetric warfare that have plagued Israel for decades. The problem was sustainability, when enemies could launch crude rockets costing mere hundreds of dollars, forcing Israel to respond with interceptor missiles worth tens of thousands. This created an unsustainable equation where attackers could potentially bankrupt defenders through the sheer volume of cheap threats. The scale of the problem became clear in the early 2000s as military strategists watched Iron Dome interceptors, each costing between $40,000 and $100,000, destroy Hamas rockets that cost less than $800 to manufacture. The mathematics were terrifying. A sustained barrage of even primitive weapons could overwhelm any missile-based defense system, not through technological superiority, but through pure economic attrition. Rafael Advanced Defense Systems, Israel's premier defense contractor, had been quietly investigating directed energy weapons since the 1990s. The company's scientists understood that the only way to break this economic stranglehold was to eliminate ammunition costs entirely. The name Iron Beam is a nod to the Iron Dome, what it did for Israel, and how this new weapon is believed to be a continuation of that success story. Just as the Iron Dome created an invisible shield over Israeli cities using kinetic interceptors, the Iron Beam would extend this protective umbrella using pure energy. Unlike the Iron Dome's parabolic trajectory calculations and explosive warheads, the Iron Beam operates on fundamentally different principles. Where Iron Dome interceptors must accelerate, navigate, and physically collide with targets, laser weapons deliver their destructive energy instantaneously across any distance within their effective range. This represents perhaps the most significant advancement in defensive warfare since the invention of radar. And the technology comes just in time. The drastic advances in drone technology have made offensive weapons wielded by Israel's enemies cheaper, faster, smarter, and more reliable than ever. Commercial quadcopters, available for hundreds of dollars, could be weaponized and deployed in swarms that traditional missile defenses simply couldn't handle cost-effectively. Iran's provision of loitering munitions for proxy forces across the Middle East created scenarios where Israel faced hundreds of simultaneous low-cost threats, exactly the kind of mass attack that could overwhelm conventional defenses. Rafael had a eureka moment when they realized the solution wasn't just about building a more powerful laser, but about diving deep into what had prevented other laser projects from working in long ranges. Atmospheric distortion, the same phenomenon that causes stars to twinkle, traditionally scattered laser beams, preventing them from maintaining lethal energy density at operationally relevant ranges. But now there was a solution. From science fiction to the battlefield. The fundamental obstacle wasn't generating powerful laser light, a technology that's existed in industrial applications for decades, but rather maintaining beam coherence and energy density across kilometers of turbulent atmosphere. Traditional approaches attempted to compensate for atmospheric distortion through brute force, using increasingly powerful lasers to overcome energy losses. Israeli scientists took the opposite approach. Instead of fighting atmospheric conditions, they would use them as a targeting mechanism. The result was known as inverse adaptive optics, a setup which, instead of trying to focus more energy in a single spot and hope it makes it farther, splits the laser's energy into hundreds of individual probe beams, each with unique parameters, including frequency, phase, and polarization. As these beams propagate toward a target, atmospheric conditions distort them differently. Some beams successfully navigate the turbulent air and reflect back to the laser source, carrying vital information about which parameters successfully penetrated the atmospheric interference. This returning data allows the system to rapidly reconfigure all subsequent laser emissions, essentially programming the entire array to follow the atmospheric path of least resistance. The process occurs continuously in microseconds, with the system constantly adapting to changing conditions. This ensures maximum energy delivery throughout the engagement, maintaining lethal power density even as atmospheric conditions shift. This has allowed Rafael to create an entire family of cutting-edge focused energy weapons. The tactical light beam functions at 10 kilowatts and is intended for mounting on vehicles to provide close-range defense against drones and smaller aerial threats in combat zones. In the latest conflict, prototypes of the light beam effectively targeted 35 Hezbollah drones, demonstrating the concept's effectiveness on the battlefield. The mobile Iron Beam M scales up to 50 kilowatts with a 250mm aperture beam director, providing battlefield commanders with deployable laser defense for protecting maneuvering forces. The full-scale Iron Beam represents the pinnacle of current technology, delivering 100 kilowatts through a 450mm aperture beam director, capable of engaging threats up to 10 kilometers away. What makes these systems a real breakthrough in military history isn't just their power, but their integration capabilities. Advanced detection systems with inherent classification algorithms enable ultra-short engagement cycles and threat prioritization. The targeting cycle includes detailed visual analysis of potential targets, dramatically reducing friendly fire risks compared to conventional missile systems that rely primarily on radar signatures. Rafael's proprietary coherent beam combining technology enables multiple laser sources to function as a single, more powerful system, while simultaneously compensating for atmospheric distortion. This approach provides redundancy and scalability. If one laser module fails, others continue operating, and additional modules can be added to increase total system power. This detection and engagement process operates at superhuman speeds. Radar systems identify potential threats and calculate intercept points, while electro-optical sensors provide visual confirmation and precise tracking data. Once a target is confirmed hostile, the laser system locks on and begins the atmospheric probing process, typically destroying the target within seconds of initial detection. Perhaps most remarkably, these systems can engage multiple targets simultaneously. In contrast to most missile-based defenses, which require individual interceptors for each threat, laser weapons can quickly switch between targets, engaging them in a sequence faster than human observers can track. This capability proves particularly valuable against drone swarms or coordinated attacks designed to overwhelm traditional defenses. In the field, the transition from laboratory prototype to combat deployed system occurred with unprecedented speed, driven by the urgent realities of ongoing conflict. Unlike most military technologies that require decades of testing and refinement, Iron Beam systems moved from successful demonstrations in 2022 to active battlefield deployment within 3 years. The first operational deployments occurred during Israel's Swords of Iron War, beginning in late 2024. Israeli Air Force aerial defense units operated several high-energy laser weapon system prototypes, achieving what Brigadier General Daniel Gold called, quote, large-scale operational laser interception capabilities, a world first in military history. Combat results exceeded even optimistic projections. Light beam systems achieved outstanding interception rates against Hezbollah's loitering munitions, weapons specifically designed to evade traditional air defenses through unpredictable flight patterns and small radar signatures. These successes validated years of theoretical work and computer modeling, proving that laser weapons could operate effectively in real-world combat conditions. Traditional Iron Dome batteries can be overwhelmed by sustained attacks, requiring dangerous resupply operations or accepting reduced defensive coverage as ammunition stores deplete. Laser systems, constrained only by power generation and cooling capacity, maintain defensive coverage indefinitely as long as their supporting infrastructure remains operational. The economic implications proved equally dramatic. While Iron Dome interceptors cost between $50,000 and $100,000 each, laser engagements cost approximately $3 per shot, essentially the cost of the electrical power consumed. This economic transformation effectively eliminates the attacker's traditional advantage of using cheap weapons to drain expensive defensive resources. Lightspeed warfare. The operational data gathered during these initial engagements will drive the next generation of improvements and likely accelerate adoption by military forces worldwide. Lockheed Martin's partnership with Rafael signals the globalization of laser weapon technology. The American defense giants' teaming agreement for developing, testing, and producing high-energy laser weapon systems in both the United States and Israel indicates that directed energy weapons are transitioning from experimental Israeli technology to mainstream military capability. The implications extend far beyond air defense. Rafael insiders say this breakthrough marks a major scientific leap, bringing together expertise from multiple fields. Lasers have been around for decades, mostly in short-range roles like precision surgery. But showing they can work effectively over kilometers opens the door to all kinds of new military and civilian uses. Mounting lasers on aircraft is still a tough challenge. When both the weapon and the target are flying, elements like turbulence, smoke, and dust can throw the beam off. Still, Rafael believes that now that ground-based systems are proving viable, airborne ones might not be far behind. Of course, any new weapon brings a new wave of countermeasures. But maybe the biggest shift isn't tactical, it's economic. If lasers make air defense cheaper and more accessible, countries that couldn't afford to field missile interceptors might suddenly have a real option. That could reshape global military strategy in ways we're only beginning to understand. This could alter regional power balances and reduce the effectiveness of traditional missile-based deterrent strategies. As Rafael prepares to deliver the first production of Iron Beam systems later this year, military planners worldwide are reassessing fundamental assumptions about offensive and defensive capabilities that have governed warfare for generations. The age of light-speed warfare is here.